Okay, so this video is going to go over how to crunch the numbers for the Hill reaction data that you collect in lab. So you understand why we're crunching the numbers the way we are, why we're presenting the data we are, and you can refer back to this video as you write your lab report for this project. So if you remember, oxidized DPIP has an absorption maximum at or near 600 nanometers. It's in the blue. So when it's oxidized, DPIP appears blue, and it's going to absorb a lot of that wavelength of light. When it's reduced, it does not absorb light at that wavelength. In other words, it turns colorless, and light will pass right through, which will change the amount of absorbance. As DPIP is scavenging electrons from the electron transport system, the solution decreases absorption at 600 nanometers, and we're going to collect absorbance measurements at specific times, starting at time 0, at 5 minutes, at 10 minutes, at 15 minutes, maybe at 20 minutes. So through time, we're going to collect absorption data from our different conditions. So if we just take a set of data, it looks something like this. Now you could put that in your paper, and I would look at that and go, ugh, because I'm going to have to think a lot about this. Couple things. In scientific papers, raw data never really belongs. Unless your instructor specifically tells you to include raw data, don't include raw data. It's hard on the reader. The reader has to look at this and go, okay, what does this really mean? And you kind of have to do some math in your head, and it's painful for the reader. A scientific paper should be easy to comprehend by your reader. It's an argument. You're trying to convince your reader of something. Either you're trying to convince them that your hypothesis is supported, or you're trying to convince them that your hypothesis was not supported, but you're trying to convince them. And the more work that they have to do, the less convincing your argument is. So you think, all right, cool. This is hard to read. It's a bunch of numbers in a spreadsheet. Let's just graph it and see what that looks like. Okay, so here's our graph of it. Here on the y-axis, we have the absorbance at 600 nanometers. Down here, we have the time scale. That's all good. It's graphed here as a scatter plot with lines. And that way we can follow each experimental condition and each control through time. That probably works best, certainly better than a column graph or a pie chart or even just a simple line graph. This is a scatter plot with lines, and that's probably the best way to display this data. However, I look at this and I see a bunch of lines going different directions, and it's kind of hard to compare one to another. To really understand what's going on, if I really wanted to know which of these experimental conditions the Hill reaction was working the best in, or probably more appropriately was working most efficiently in, it's really hard to tell from this graph. And this graph doesn't really represent what we want to know anyway. What we really want to know is what is the change in absorbance over time. Not just what is the absorbance over time, but what is the change in absorbance. And we can do that with this very simple equation. What was the absorbance at time 0 minus the absorbance at different time points, so T sub I is the absorbance at different time points, and that will give you the change in absorbance. So we'll start with a whole new graph here, a whole new table rather. So again, we have our time in minutes up here, 0 minutes, 5 minutes, 10 minutes, etc. And our controls and experimental conditions. First thing you want to do is take 0.701 and subtract it from itself, and that will give you 0. And then work your way down that column, and they will all turn to zeros. Ultimately, when we graph this, that means all of the lines will have the same exact starting point, which will make everything much clearer. Then you take 0.701 minus 0.705 and put it in that cell, and 0.656 minus 0.664 and put it in that cell, etc. And you come up with those numbers. Then take time 0 minus times 10, time point 10, and put those in this column, and you carry that all on out, and you have your crunched data. Okay, this data is the change in absorbance over time. One thing to note, you don't want to take time point 0 and subtract time point 5 from it, and then take 5 and subtract 10 from it. You want to always start with time 0. So that will always be this column, and then subtract these columns from that. So if we move this up here, here's our crunch data. This is the change in absorbance over time. And when we graph that with a scatter plot with lines, again, now our y-axis is the change in absorbance at 600 nanometers. And our x-axis is still time. Now, what this tells us here is very easy to read. Our two controls all bounced right around 0 change across time. That's what we expected. Our controls shouldn't change over time. But then we look at our experimental conditions, and it's very easy to see here that the experimental condition 3 showed the most efficient Hill reaction, and experimental condition 1 showed an intermediate efficiency of the Hill reaction, and experiment number 2 had the least efficient Hill reaction. All of that is much clearer to read than our original. So this was our original raw data just graphed. Very difficult to tell which of our experimental conditions was most efficient. And just looking at this, I probably would not have guessed that it was experimental condition 3. When we look at the change in absorbance over time, now we can really see the differences. So if you have any questions about how we did this or why we did this, please come in to see me before you write your papers, and I'll be happy to go through it and hopefully explain it a little better. But that's all there is to it.